Hello everyone, and welcome back to some more remote learning. In today's video, we're going to do some examples on graphing functions by hand. So let's fill in the table relating the first and second derivative to f of x. So summarizing everything we learned in that previous worksheet. So when f prime of x is positive, meaning that it's greater than 0, then we know our function is increasing. When that derivative is negative, we know our function itself is decreasing. And when it's 0, we know we're at a critical point. So when the second derivative is positive, remember, second derivative relates to the concavity of the original function. So when the second derivative is positive, greater than 0, that means we're concave up. And when it's negative, we're concave down. And when we're at 0, that's considered an inflection point, where that concavity changes. So not only will we use the information above that we learned in that previous worksheet, but we're also going to use information regarding the function itself when we go to graph, such as the domain. So let's recall a couple of these important concepts below before we jump into graphing. So roots. What exactly are roots? Those are the zeros of the function. So when our original function crosses the x-axis, those are the roots of our function. So this is when f of x equals 0. And those are easy things to graph. Next, we'll go over holes. Holes, remember, are when our function is undefined and the limit exists. So f of x is undefined, and the limit as x approaches that hole, let's call this x approaches a, of f of x exists. And this occurs when we have, for example, a rational function where we have some factor in our denominator that makes our denominator 0, but we can cancel it out with a factor in the numerator. That's how we get a hole. A vertical asymptote, again, is where our function is undefined, but where the limit does not exist. So we're heading towards positive infinity, negative infinity, or a combination of the two. So again, f of x is undefined, and that limit, as we approach that point, does not exist. And then lastly, we're going to go over horizontal and slant asymptotes. For horizontal and slant asymptotes, remember that was when we took the limit as x approaches infinity, either positive or negative, and our function, well, if it approaches some finite value L, our horizontal asymptote occurs at L, or if the limit of f of x as x approaches infinity is in the form of mx plus b, where it's still is technically heading towards infinity or negative infinity, however, it's tracking along a line. So if we take the limit of f of x as x approaches infinity or negative infinity, and we get some finite value, then our horizontal asymptote is that y equals L. If, as we approach positive or negative infinity, if we have a rational function where the numerator is 1 degree higher than the denominator, again, the slant asymptote was very specific, so if you don't remember all the details, refer back to that worksheet or refer to the definition in your book, but it's where the numerator is exactly 1 degree higher than the denominator, that's when our slant asymptote occurs, and that's going to be that y equals mx plus b. So even though our limit still is going to equal some infinity or negative infinity, we're tracking along some y equals mx plus b. Now for this worksheet, we have two examples, example 1 and example 2, where we're going to just be graphing functions. So we're going to use a combination of all of this information just to attempt to draw the most accurate picture of the function that we can. So f of x equals x cubed minus 4x. A good place to start is, let's use the tools that we learned in the last worksheet, when our function is increasing and decreasing, and that concavity. So we'll find critical points, and then we'll find inflection points. And before we jump into that, let's double check. What's our domain? Well, there's nothing restricting our function. X can be all real numbers. So taking f prime of x, we're going to get that 3x squared minus 4. And then when we take the second derivative of x, we're going to get 6x. So what we're going to see first is when our derivative equals 0. When does 3x squared minus 4 equal 0? Well, that is going to be when 3x squared equals a positive 4, which is going to be when x squared equals 4 thirds. So that's going to occur at plus or minus root 4 over 3. So our critical points are when x is equal to plus or minus root 4 over 3. So now would be a good time to maybe type this into a calculator just to get an idea of roughly where this occurs. So 4 thirds we know is 1.3 repeating, and if we take the square root of that, that's going to be about 1.15, and that's a positive 1.15 and a negative 1.15, and that's with a little bit of rounding. So we have 2 critical points at the moment. Let's see when our second derivative equals 0. That's going to occur when x equals 0. So if we were to draw our number line, like we did in our previous problem, at negative 1.15, 0, and then a positive 1.15, we have critical points, and we have an inflection point. So I'm going to look at the second derivative, and I'm going to look at the first derivative, deciding when each of those is positive, negative, and we already know when they're 0. So let's first look at that second derivative, since we only have 2 potential options. We have to the left of 0, and we have to the right of 0. To the left of 0, what kind of numbers would those be? Those would be negative numbers. If I plugged in a number to the left of 0, negative 1, I'm going to get a negative 6. So my second derivative is negative to the left of 0, and to the right of 0, it's going to be positive. Now, let's look at my first derivative, because I know now when my function's concave down and when it's concave up. Now I'm going to decide when it's increasing or decreasing. So looking up above, back at my first derivative, if I plugged in a number to the left of negative 1.15, let's say negative 2, negative 2 squared is going to be a positive 4. 4 times 3 is 12. 12 minus 4, that's going to give me positive values. Now I'll plug in a value in between my 2 critical points, which is 0. I'll just go ahead and use that inflection point. Plugging in 0, I'm going to get a negative, because 3 times 0 squared is 0, minus 4, that's going to give me a negative. And then to the right of 1.15, plugging in a positive, let's do 2. 2 squared is going to be 4. 4 times 3 is 12, minus 4, that's going to be a positive number. So now I know that I'm increasing in concave down, then I'm decreasing in concave down, then I'm still decreasing, but I switch to concave up, and then I'm concave up and increasing. So I know roughly the general shape of my function. Let's go ahead and fill that in. Increasing concave down, decreasing concave down, decreasing concave up, and then lastly, increasing concave up. So it looks like our function is going to have a maximum at negative 1.15 and a minimum at 1.15. But before we actually go to graph this, we want a little bit more information so that we can fill in our function accurately. And one thing that might be nice to know is exactly what is our minimum and maximum value. So when I plug in negative 1.15 or negative root 4 over 3, what do I get for my function value? Plugging those in quickly to a calculator, I get negative 1.15, comma, that's about 3.08, and then when I'm at positive 1.15, I'm at approximately a negative 3.08. And when I'm at my inflection point of 0, if I plugged 0 in to the function, I'm going to get 0. So then my inflection point occurs at 0, 0. So let's go ahead and plot those points now. So negative 1.15, I'll put negative 1 here, then negative 2, and then I'll put positive 1, positive 2. I know my inflection point occurs at 0, 0, that's where my concavity switches, and then at about negative 1.15, I'm about a positive 3.08. So I'll go up to about here, and I'll label this about 3. So we have 1, 2, 3, 4, 5, this will be 6, and then 1, 2, 3, that'll be my negative 3, and then 4, 5, 6 to negative 6. So then when I'm at a positive 1.15, I'm at about a negative 3.08. Another great thing to find would be the roots of this function. So when do I cross my x-axis? I know already one of my roots is 0, 0, and I'm concave down until that point. So my function looks something like this, and then at that point I switch and I become concave up. But what exactly happens past that? Well, I know that I'm concave up and positive going towards infinity, so I know that I'm going to eventually be approaching a positive infinity towards my right, and then as I go towards the left, towards negative infinity in the x, I'm going to be approaching a negative infinity in the y. I pictured that over here already. But a great piece of information would be to know my roots, because then I know exactly when I'll cross that x-axis. So figuring out my roots, when does f of x equal 0? So when does x cubed minus 4x equal 0? Well, I'll factor that by pulling out an x and get x squared minus 4. When does that equal 0? Well, we already know that occurs at least at x equals 0, but it also occurs when x squared minus 4 equals 0. So when x squared minus 4 equals 0, that means that x squared is equal to 4. Which means x is going to be equal to a positive or negative 2. So those are my other two roots in my function. So we have negative 2, and then we have positive 2. And there we have it. That's what my function looks like. Now remember up above, we talked about holes and vertical asymptotes, and both of those occur when our function is undefined. But in this example, we don't have any x values that will make our function undefined, so we're not going to have any holes or any vertical asymptotes. The other piece of information we talked about was slant or horizontal asymptotes, and that occurs as if we go towards a positive infinity or a negative infinity, we're approaching some finite value, or we have some rational function where the degree of the numerator is 1 more than the degree of the denominator. That's not the case at all in this example, because as we approach positive or negative infinity, our function approaches positive and negative infinity. But this is the graph of the function. And if you want an even more accurate graph, maybe go out past 2 and past negative 2 and pick another point and try to plot that, just so you get a little bit more of the shape of the arc and the way the curve forms. However, for our purposes, this is a great job for example 1. Let's continue on to example 2. And I thought it'd be nice to quickly show you what exactly this graph looks like. You can see there is my f of x. Eventually I'm going to show you what g of x looks like, but for now, here's my f of x. And you can see we did a pretty good job. We got our roots at negative 2, 0, and positive 2. We also have our correct mins and maxes, and our function continues towards infinity and negative infinity. So once you graph it by hand, graphing it online is a great double check. Let's continue on to that next example though. Moving right along, in example 2, we're going to graph the function of g of x. G of x is x squared minus 5x plus 4 all over x plus 1. So we're going to have a little bit more information to find in this because we're going to get some undefined values. Like up above, let's start by finding our critical points and inflection points. But before we go on, I want to make a note that x cannot be equal to negative 1. So when we're approaching x equals negative 1, we're either going to have a hole or we're going to have a vertical asymptote, which we'll look at later. But I just wanted to make that note so we don't forget. So let's start by finding that first derivative in order to find the critical points. What are we going to do? Low d high minus high d low all over low squared. So that's going to be low d high minus high d low all over low squared. Now let's try to simplify this down a bit. X times 2x goes to 2x squared, and then we have minus 5x plus 2x minus 5, and then we're subtracting x squared, and then we're subtracting a negative 5x, so that'll be plus 5x, and then we're subtracting 4. And that's all over our x plus 1 squared. Notice that minus 5 cancels out with this positive 5, and then we have negative 5 minus 4, which is going to be a negative 9. So this simplifies down to 2x squared minus x squared, which is x squared plus 2x minus 9. And that's all over x plus 1, that quantity squared. And we're trying to see when exactly this equals 0. Now remember, x can't be negative 1, so when we multiply that over, we're not going to lose anything valuable, so to say. But I'm going to just see, if I do multiply that over, when does x squared plus 2x minus 9, when does that equal 0? And I don't think this is going to be done by factoring, so let's go ahead and do the quadratic formula. So x is going to be equal to the opposite of b, plus or minus the square root of b squared, which is 4, minus 4 times a times c, so that's 4 times 1 times negative 9, all over 2a, which becomes a 2. So we'll get negative 2 plus or minus the square root of 4 times negative 9 is a negative 36. 4 minus a negative 36 is going to be 4 plus 36, which is going to be the square root of 40, all over 2. This simplifies down into negative 1 plus or minus, if I was to pull a 4 out of this, because 4 is a perfect square, that's going to give me 2 root 10. 2 root 10 over 2 is going to be plus or minus root 10. So that was simplifying down and splitting up that fraction. Let's go ahead and enter this into our calculators now. Negative 1 plus root 10 is going to give us approximately 2.16, and negative 1 minus root 10 is going to give us about negative 4.16. So those are our critical points for our function, potential max and mins. And let's go ahead, because we have those x values, let's find their full point values so we know exactly where our potential max and mins occur. So if I enter in negative 4.16 and I enter in a 2.16, I'm going to get function values that are negative 13.33 and negative 0.68. So these are my critical points. Now I'm going to find my inflection point. So going back up to this simplified derivative, I'm going to calculate g double prime of x, which is going to be a little bit of the quotient rule again. So we have our low, which is x plus 1 squared, d high, so that's going to be 2x plus 2, minus high, which is x squared plus 2x minus 9, times the derivative of our low, so we're going to need to do a little bit of chain rule, bringing that 2 down in front, multiplying by x plus 1, that's all raised to the first, and then multiplying finally by the derivative of that inside, which is 1. So I don't even need to raise this to the first or write 1, I'll leave it like that, and that's all over x plus 1 squared squared. So x plus 1 squared squared becomes x plus 1 to the 4th. Let's go ahead and see if we can simplify this down a bit. Notice that if I was to distribute this 2 into here, I have a 2x plus 2. So 2x plus 2 is actually a common term. So if I pull my 2x plus 2 out in front, then I'm going to multiply that by x plus 1, that quantity squared, minus x squared plus 2x minus 9. and that's going to be all over x plus 1 to the 4th. Now, simplifying that numerator a bit more, I'm going to leave my 2x plus 2 out in front, but I'm going to expand out that x plus 1 squared. That's going to be x squared plus 2x plus 1. And I'm subtracting, from that, I'm subtracting x squared plus 2x minus 9. So if you take a look at this, my x squared is going to get canceled out in my numerator, and so is my 2x. So I have 1 minus a negative 9, which is going to be plus 10 in my numerator. So in my numerator, I have 2x plus 2, and that's multiplied by 10, because I have that 1 minus a negative 9, which goes to 10, and that's all over x plus 1 raised to the 4th. And remember, what are we trying to do? We're trying to see when this is equal to 0. Multiplying both sides by x plus 1 to the 4th, that'll cancel out, and then dividing by 10, I'll still just have 0 on my right-hand side, so I'm going to see when 2x plus 2 equals 0, and that occurs when 2x equals negative 2, which is when x equals a negative 1. So my inflection point is when x equals negative 1, and remember, at negative 1 I'm undefined. So I don't have a value for negative 1, but I know that it's an inflection point. So continuing on to the next page, or flipping to the back side, we're going to finish graphing this. So let's go ahead and draw out our number line to figure out when we're increasing, decreasing, concave up, and concave down. So my points are negative 4.16 as a critical point, and then 2.16 as a critical point, and then my inflection point occurs at negative 1. So my second derivative I'll put at the top, and my first derivative will be at the bottom along my number line. So starting with that second derivative, because I only have two potential options, when I'm to the left of negative 1, let's go back to the most simplified version of this before we set it equal to 0. So right here, I'll get rid of canceling those out. When I'm to the left of negative 1, I'm going to have a negative numerator, and my denominator is always positive because I'm raising it to an even power. So to the left of negative 1, I'm concave down, and to the right of negative 1, I have a positive numerator and a positive denominator. And again, if I plugged in negative 2, I would get a negative, whereas if I plugged in, let's say 0, I would get a positive. Now we're going to go back to the first derivative and look at plugging in values to the left of negative 4.16, in between negative 4.16 and 2.16, and then to the right of 2.16. So first of all, looking at values to the left, if we go to our simplified derivative here, values to the left, that's going to be a positive in my numerator, and my denominator is always positive. So that's going to be positive. And then if I was to plug in a value between that negative 4.16 and 2.16, let's say 0, I'm going to get a negative in my numerator. Negative over a positive is going to give me a negative. And then lastly, if I plug in values to the right of 2.16, that would be, for example, 3. You can see 3 squared minus 9 goes to 0, but then I have a positive 3 times 2, which is going to give me a positive. Again, over a positive is going to be a positive. So I figured out when my function is increasing and decreasing, and when it's concave up or concave down. So thinking about how this potentially looks, I'm increasing and concave down up until negative 4.6, and then I'm concave down and decreasing. But then, to the right of negative 1, I'm decreasing and concave up. And remember, I'm undefined at this point, so that's either going to be a hole or it's going to be a vertical asymptote. I don't know which one yet, but I'm going to decide up above. And then to the right of 2.16, we're concave up and positive, like so. So let's move on to looking at our roots really quickly so that we can get a pretty good graph to start. My roots are when my function equals 0, and that's when x squared minus 5x plus 4. When does that equal 0? Because if my numerator equals 0, then my overall function equals 0. I can factor this. X squared minus 5x plus 4 factors into x minus 1 times x minus 4. So my roots occur at x equals 1 and x equals a positive 4. So when I'm at those points, my y value is 0. So 1, 0 and 4, 0. Let's go ahead and start filling in a couple of these points below. So remember, our inflection point was at -1, and at -1, we either have a vertical asymptote or a hole. So I'm going to make a note that this is -1. Our maximum value occurred at -4.16. So when I go over to -4.16, and obviously this isn't the most accurate, but I'm labeling all my critical information, I have a maximum at a -13.33. So I'm going to go all the way down to here, and I'm just going to mark this as -13.33. There's my maximum, and I'll do this in red. Then I also have a minimum at 2.16. So when I go over to 2.16, roughly, then I'm at a minimum of -0.68. So getting that maximum value just below the x-axis, there we go, at that -0.68. And then, don't forget, we found those roots. That was at a +1 and a +4. So I'll make a note that that was 4 and this is 1. So I know that based on my rational function up above, the limit as x approaches infinity is going to be positive infinity, and as we approach negative infinity, it's going to be a negative infinity. And again, that's because the degree of my numerator is greater than the degree of my denominator. So I know I'm approaching either infinity or negative infinity. But remember about that slant asymptote? Our degree is exactly 1 higher than our denominator. So we have a slant asymptote. How do we find that slant asymptote? We're going to divide. So a little bit of polynomial long division. X squared minus 5x plus 4, dividing that by x plus 1. X plus 1 goes into x times, that'll leave me with x squared plus x, but I'm subtracting that entire quantity, so that'll be -5x minus x, that's -6x, and then I'll bring down that plus 4. So then x goes into -6x, -6 times, -6 times x plus 1 is going to be -6x minus 6, but again, remember I'm subtracting that, that goes to 0. 4 minus a -6, that's going to be plus 10. So simplifying this down, I'm going to get x minus 6 plus 10 over x plus 1. And if you can think about taking the limit of this function as x approaches infinity or negative infinity, this is approaching 0, so my linear equation or my slant asymptote is y equals x minus 6. So I have my slant asymptote, I have my critical points, I have my inflection points, I have my roots. Now I just need to figure out that x equals -1. Is it a hole or is it a vertical asymptote? And we can kind of already see how this function develops right here. I'm coming down and I'm making that minimum, and then I'm tracking along my slant asymptote, which had an intersection point of -6, so roughly about here, and that slope was a +1, so I know that it's going to cross my x-axis at a +6. So connecting those dots, there is my slant asymptote. So you'll see that that's going to track along that. So coming from the left to my maximum, and then I'm going to start going down. And because I'm concave down up until -1, and then to the right of that I was concave up, that's going to be a vertical asymptote. at -1. So towards -1, I'm going towards infinity, and towards -1 from the left, I'm going towards a negative infinity. And that's what my graph is going to look like. I'll go ahead and draw my vertical asymptote in green. And we can confirm this vertical asymptote because if we go back up to our function, and to confirm that vertical asymptote, let's take the limit of g of x as x approaches a -1. I know that my denominator is approaching 0, and if I'm coming from the left, it's approaching 0 from negative values. If I'm coming from the right, it's approaching 0 from positive values. So my sign is going to be different in my denominator depending on if I'm coming from the left or from the right. And looking at my numerator, approaching from the left, values very close to -1. As I approach from the left, those values are going to be positive. Whereas I'm approaching from the right, those values are going to be getting closer and closer to -1. Those are going to be positive as well as we approach that -1. So positive over negative, as I'm approaching from the left, I'm going towards negative infinity. Positive over positive, as I approach from the right, I'm going towards positive infinity, which now confirms that vertical asymptote, where one side's going towards positive infinity and the other is going towards negative infinity. So my graph looks something like this. And let's go ahead and see the real thing to double check. There we have it. A little bit more accurate, but you can definitely see that slant asymptote of x minus 6. You can see that line and how that function hugs the line as it approaches positive infinity and as it approaches negative infinity. But with that, we wrap up this graphing functions worksheet. Remember, you're always going to want to check your roots of your function as well as horizontal, vertical, slant asymptotes, and then also potentially holes. Once you gather that information with your function and use the information you gathered from your derivatives, you're going to be able to graph a pretty accurate picture of your functions. And I know the second example was rather long and took a lot of time, but it was very valuable to look at each of those different parts, and you'll be able to carry that information forward when we talk more about derivatives. Continue on to the next video, but until then, good luck with your online learning.